Okay. Chapter 8, internal forced convection. It has 6 parts. First part is the introduction. Then there's going to be the average velocity and temperature that's going to be considered. Then the entrance region. 8.4, general thermal analysis. Laminar flow in 8.5 and 8.6 is turbulent flow in tubes. So that is an overview of the chapter. So let's start with the introduction of chapter 8. And it starts by making it a little bit more clear the nomenclature which is going to be used quite a lot, especially in this chapter, because we work with internal forced conduction. Because we work with internal flow, usually we have a boundary all around the flow. And in most cases, it can be limited to, firstly, something like this, which has a circular shape. Okay, a circular shape, and it is called a pipe. Especially for liquids. And it is called a tube for small diameters. Okay. So if the diameter is small, then usually we refer to it as a tube. Larger diameters, usually pipes. And if the geometry is circular, in general, a pipe. If it has another type of geometry, maybe something like this, which is non-circular, then it is referred to as a duct. In mechanical engineering, about 99% of our flows occurs through either tubes or ducts. Usually ducts in the air conditioning and the refrigeration industry, where air is being moved through a building. The characteristic of a pipe is that it can withstand very large pressure differences. So if there's a large pressure difference between those values, then that is specifically the reason why we prefer to use pipes. It can take very large pressure differences. Ducts usually cannot. Usually air is being pumped through it, and usually the pressure differences are very, very small. So this is in general the nomenclature that is being used. Paragraph 8.2 is on the average velocity and temperature. Average velocity and temperature. It's a little bit of revision in terms of fluid mechanics, but we want to connect it now to heat transfer also. And in fluid mechanics, if we've considered flow through a pipe or a tube, then we know that there's a boundary layer that develops. There's a boundary layer that develops, and in this region, in the entrance region, this velocity here would be the same as the inlet velocity. So that would be the irrotational flow part, and that would be the boundary layer, and the velocity profile would look like that. So in general, the velocity is a function of r. It's a function of r. If it is fully developed, then the velocity profile would look like this. Parabolic, if the flow is laminar. If not, if it's turbulent, then it would look like something like that. So there are two different possibilities. But again, the velocity is a function of r. Now what we normally work with is not with the specific values of the velocity, but with the average velocities. So if we do the integration here, then that would be equal to U average. And that would be exactly the same as that average value there. So the average value would remain constant from the inlet to the outlet. It doesn't change. So in general, we would say that the mass flow rate is equal to the density multiplied by either V average or U average, whichever one you want to use. Let's rather change that to V average, multiplied by the cross-sectional area, or it can be written as the integral over the area of rho multiplied by U, which is a function of R, and integrate over the cross-sectional area. The details of that you can go and look in the fluid mechanics part. That is just a little bit of revision. So what we're saying is that in essence that this average velocity, if we do the integration, can be written typically as 2 times divided by R squared, where R would be equal to that radius there. R is the radius of the tube, multiplied by the integral from 0 to R of U integrated over the radius. So that is the average velocity. Okay, now in heat transfer, in 99.99% of the cases, we are not going to get involved in this integration. We are just going to use the average velocity. That is what we're going to use for the calculation of our problems. Now the same with the temperature. If we look at the temperature in a tube, and let's suppose this distance is a representation of the temperature, the absolute temperature. Remember, it's not a vector. For that reason, we just show it as lines. So the longer the line, the higher the temperature. Now let's suppose this is Ts and that is Ti, and the surface temperature is higher than the inlet temperature of the fluid. Okay, what is going to happen now is that the temperature distribution is going to look at the inlet at something like this. The surface, the temperature is going to be higher than that on the center. And after a very long time, after it has been fully developed, then everything would be the same. Okay. Okay, and this we actually call Tm. Sorry, that is not Ts. That is equal to Tm. Okay, and I'm going to describe to you what Tm is just now. So Tm is equal to, and I'm not going to do all the mathematics, but it is 2 times the average velocity multiplied by R squared, the integral from 0 to R of the temperature multiplied by the velocity distribution R dr. So we can see that the mean temperature is a function of the velocity distribution. Okay, and what we normally also do is we say that the fluid properties, the fluid properties we are normally interested in is the density, the viscosity, the Cp value, the Prandtl number, etc. Those properties we calculate at the bulk temperature. Calculate it at the bulk temperature, where the bulk temperature is equal to the inlet temperature plus the outlet temperature divided by 2. Okay. So to make this a little bit more understandable in terms of this mean temperature and the S temperature, etc., let's suppose we have flow through a tube, and that is the inlet temperature and that is the outlet temperature, and this tube is being heated, and here is a fire. Okay. Here is radiation heat transfer. Okay. Here is maybe condensation, different types of heat transfer that occurs on the surface. If we now plot the temperature as a function of x, okay, so that is x measured from the inlet, then that is going to be the inlet temperature, and depending on the type of heating mode, the temperature might do something like that. So that is equal to the inlet temperature, and that is equal to the outlet temperature. Okay. This temperature here, at that point there, is the mean temperature, which is a function of x. Okay, so at that point there, so it is the average temperature taking into consideration the velocity profile. Okay, so it's the average temperature taking into consideration the velocity profile. And the bulk temperature is then equal to the inlet temperature plus the outlet temperature divided by 2, which is going to be approximately that temperature there. Okay. So the bulk temperature is not the mean temperature. Okay. The bulk temperature is just the average of the inlet and the outlet. The mean temperature varies throughout as a function of x, but it doesn't vary in the r direction. We consider it as a constant in the r direction. You follow that? Okay, so we're making things easier, not more difficult. Okay, now laminar and turbulent flow. Laminar and turbulent flow in tubes is the next section. And we've already discussed it, saying that we use the Reynolds number to tell us if the flow is laminar or turbulent. The Reynolds number is equal to rho multiplied by the average velocity multiplied by the diameter divided by the viscosity. Or we can write it as the average velocity multiplied by d divided by the kinematic viscosity. And we can write the Reynolds number also in different formats. An example is specifically if we say we know that the mass flow rate is equal to rho multiplied by the area multiplied by the average velocity. And if we look there, we can see there's a density multiplied by the velocity, a density multiplied by the velocity. So we can say that the density multiplied by the average velocity is equal to the mass flow rate divided by the area. Okay. So if we substitute this now into the Reynolds number, we substitute that in the Reynolds number, then, before we do that, let's rather write it first as the mass flow rate. divided by the area, and the area would be equal to pi divided by 4 multiplied by d squared. Okay? And that would now be specifically for a circular tube. Okay, for a circular tube. So we can then say that the Reynolds number is equal to, if we do that substitution, the mass flow rate multiplied by the diameter divided by pi divided by 4 d squared multiplied by the viscosity. Therefore, we can write it as 4 times the mass flow rate divided by the viscosity, pi, and the diameter. Okay? So the Reynolds number, where previously it was written as a function of the velocity, we've just written it as a function of the mass flow rate. It is a very practical result because in many cases it's going to be given to you that the mass flow rate through the tube is so many kilograms per second. And then you can directly calculate the Reynolds number without first going to calculate the velocity. Okay, so it just saves you some time. But remember, this is only valid for a circular tube. If it's not a circular tube, then this area is not going to be pi divided by 4 d squared. Okay, so just be careful for that. Okay, so if it is a non-circular tube, then you've done it in fluid mechanics that we substitute the diameter with the hydraulic diameter. With the hydraulic diameter. Where the hydraulic diameter is equal to 4 times the cross-sectional area divided by the perimeter. Okay, so AC is the cross-sectional area. And P is the wetted perimeter. I trust you've done many examples like this in fluid mechanics, but just to refresh your memory, let's look at a rectangular duct. A rectangular duct where that is equal to A and that dimension is equal to B. Calculate the hydraulic diameter quickly for me. Calculate the hydraulic diameter for that case quickly for me. Okay, so the hydraulic diameter is equal to 4 times the cross-sectional area, and the cross-sectional area is equal to A multiplied by C. A multiplied by B, sorry. A multiplied by B. The wetted perimeter is equal to A plus B plus A plus B. You agree? It's just A plus B plus A plus B, which you can write as 4 times AB divided by 2 times A plus B, which is equal to 2 times AB divided by A plus B. Okay, you happy with that? Okay. What we've also discussed previously is the fact that the Reynolds number can be used to determine if the flow is laminar or turbulent. And we said that if the Reynolds number is smaller than 2,300, the flow is laminar. Do you agree? You happy with that? Ladies and gentlemen, no, it's not true. It's true only for a tube. Okay. For a tube or for a pipe. It is not generally true. If it is larger than 10,000, and that's going to look strange to you, but I'm going to explain it to you just now. We're going to say the flow is fully turbulent. And again, that is for a tube. It's not a general result valid for all cases. It's only for a tube or for a pipe. Okay. If the Reynolds number is larger than 2,300 and smaller than about 10,000, then it's going to be considered as if the flow is in transition. Okay, now transition, heat transfer, or fluid mechanics is a very complicated thing. We are not going to really have time to consider it in detail. But for the purposes of this textbook, that is what the author does. And what he also then say is that if the Reynolds number is larger than 4,000, then in most cases, it can also be considered as fully turbulent. Okay. So if it's smaller than 2,300, it is laminar. If it's 2,400, it's a debate if it is turbulent or not. Most probably it will be in the transition flow regime. If it starts becoming more than 4,000, then most probably it will be fully turbulent. But if it's larger than 10,000, then most probably it will be fully turbulent. Okay. Now, what is the reason for this uncertainty? Okay. It has to do with transition, how the flow changes from laminar to turbulent is being influenced firstly by quite a few things. The firstly is the type of inlet which is being used. The type of inlet. So the inlet might look like that. Okay. Or it might be something like that. Okay. Or it might be smooth, a type of a bell mouth type of inlet, and all of them will have different characteristics in terms of the transition from laminar to turbulent. But not only that, the smallest manufacturing difference will influence the transition. Okay. So the type of inlet, the geometry of the inlet, and any small manufacturing disturbance, or the fact that this length is not exactly the same as that length, will influence the transition. So that is the first influence on transition. The second one is vibrations. Okay. If I would here in my lab in this building be busy with experiments in the transitional flow regime, and the gauw train passes, then it might influence the result. Or if somebody is in a parking garage going over one of the hobbles, you've felt that vibration in the building, that will most probably also influence the transition in the tube. So that's the second one. And the third one is roughness. So all those factors influences transition. Okay, paragraph 8.3 is the entrance region. Okay. Now we've done the entrance region previously We have discussed it, but I'm going to revise some of the most important results for you. And that is firstly, by again, looking at the velocity profile through the tube. Okay. If we look at the velocity profile of a tube, we know that the boundary layer starts developing. Okay. Until the two boundary layers meet. Until the two boundary layers meet. That distance is considered as LH. The hydrodynamic entrance region. The hydrodynamic entrance region, again, if this is equal to V, then at this point here, between the two boundary layers, this velocity would also be equal to V. Okay, so that velocity and that velocity will be the same. And then, in this region, it will feel the influence of the boundary layer. So that is how the velocity profile is going to develop. And as we've already mentioned here, it is going to be fully developed, either as a parabolic velocity distribution for laminar flow, or as a Planck velocity distribution for turbulent flow. Okay. But what is important is this LH. For the thermal boundary layer, the principle is exactly the same. The two boundary layers are going to develop until they meet. Okay. And at this point, there's going to be a fully developed temperature distribution. And that distance is called LT. The thermal entrance region. The thermal entrance region. Thermal entrance region and the hydrodynamic entrance region. Now in this region here, if we look at all the shear stresses and we study the velocity profile, then the moment the flow is fully developed, then du dx, du, which is a function of r and x, dx would be equal to 0. The velocity gradient would be equal to 0 from this point onwards in the x direction. So the velocity is only a function of r. Are you following what I'm saying? I'm saying that if we look at the velocity at that point there, and at that point there, and that point there, then the velocity does not change as a function of x. Remember, x is in this direction. It is now a constant. It's fully developed. Okay. The thermal boundary layer is going to look a little bit strange, but if you go and look at the definition of the thermal boundary layer, you will see it is equal to partial ddx of the temperature on the surface x minus the temperature Rx minus the mean temperature, that is equal to 0. So the temperature gradient is equal to 0, and du dx is equal to 0 from this point on forward. Let's rather sketch it as two different graphs. In this case, we would be interested in the friction factor. So if we look at the friction factor as a function of x, then at this point here, the velocity gradient will be the largest. If the velocity gradient is the largest, then the pressure drop here would be the largest. And therefore the friction factor will be the largest. So the friction factor is very large, and then the following will happen. That point there would be equal to LH. So what we're going to do a lot in this course is we are going to refer to developing flow, while here it is fully developed flow. Developing versus fully developing. Developed versus fully developed flow. Okay. So we can see at this point here the friction factor is a constant. On this side, when we take a look at the temperature results, and we look at the heat transfer coefficient as a function of x, then we're going to have a similar result. This is going to be the distance LT for the heat transfer coefficient. And the flow on this side we are going to say is developing flow. And here it is fully developed flow. Okay, so you're going to see in this course that there are lots of formulas that you can use. Lots of formulas are given. And this is one of the most important things that you always should think of when you consider these equations. Usually they would tell you, this equation is for fully developed, turbulent, and that, etc. Okay. And then you must know, it's going to give me this result. If it's for developing, it's going to give that result. So it depends on the practical situation we are considering, which of the equations we should use and which ones are valid. In terms of entry lengths, let's first look at the case of laminar flow. The flow is laminar. If the flow is laminar, then LH, this distance, how long it is going to take before the flow is fully developed. For laminar flow, LH for laminar flow, can be written as approximately 0.05 times the Reynolds number multiplied by the diameter. This comes from measurements which shows that the shear forces are within 2% of the fully developed ones. So that is the criteria which is being used. 2% of the shear forces. For this one, LT. Okay. For LT, again, for laminar flow is equal to 0.05 times multiplied by the Reynolds number multiplied by the Prandtl number multiplied by the diameter. Okay. So coming back to these results, this distance and this distance would be the same if the Prandtl number is equal to 1. The Prandtl number is equal to 1, then those results would be the same. Let's consider the case, just two practical examples. Firstly, let's consider a very low Reynolds number. Let's suppose the Reynolds number is 20. Okay, if the Reynolds number is 20, so 20 times 0.05 is about 1. Okay. Then it would mean that LH for laminar flow is approximately 1 diameter. Okay. Just 1 diameter for Reynolds number of 20. That's very low flow. LT would be equal to 1 times the diameter multiplied by the Prandtl number. Prandtl number of air is about 0.6. So that would be 0.6 times the diameter. If it's water, the Prandtl number of water, depending on the temperature, is about 6 to 7. So then it would be 6 diameters. Okay, so that is now for laminar flow. Let's consider it for turbulent flow. For turbulent flow, it's very easy. Then LH for turbulent flow is equal to LT for turbulent flow. And that would be 10 diameters. If it's turbulent flow, it takes 10 diameters, then the flow is fully developed in terms of the velocity boundary layer and the thermal boundary layer. Okay. Let's go back to this case. To this case, if the Reynolds number is 2,300, that would now be the other extreme. If it's 2,300. If it's 2,300, then that distance would be 115 diameters. 115 diameters. And the thermal one would of course be 115 times the Prandtl number multiplied by the diameter. So if it is air, it's 115 multiplied by 0.6, it's approximately 100 diameters. If it's water, it's going to be about 700 diameters before it is fully, 700 diameters before the flow is fully developed. Okay. You follow? Okay. So many of it you've done in fluid mechanics. We just put the heat transfer part with it. Okay. Now, in heat transfer, there are two cases which are very important, which we are going to get a lot. Firstly, because there are many practical applications of it, and secondly, because we can do good experiments with it, and our theory can handle it. So there are two cases, and these two cases are firstly the case of a constant heat flux and the second one is a constant wall temperature. Constant heat flux and a constant wall temperature. Okay, the constant heat flux, if I can show it to you schematically, if that is a tube and we have flow through the tube, normally in fluid mechanics and heat transfer, the flow is always from the left to the right. Okay. Usually from left to right. And I would get a constant heat flux if, for example, so that would be equal to a constant heat flux, if I put in 50 watts per square meters of heating on that tube. Okay. Or maybe 60 watts per meter. So every meter, 60 watts is going into the tube of heat over that 1 meter. Okay. So usually we would say small q is equal to a constant. That would obviously be in units, watts per square meters. Watts per square meters. And the practical cases where we can get this type of boundary condition is firstly with electrical heating. Okay, we've got a high resistance wire which is coiled around the tube, and we've got a current flowing through it. Firstly, electrical heating. Secondly, radiation. Radiation heat transfer on that tube. And thirdly, a nuclear reaction. A nuclear type of reaction would also give us a constant heat flux on the tube. So those are the three cases that we normally consider. The other case is the constant wall temperature. Constant wall temperature is where on the outside we have condensation or evaporation, boiling. Condensation or boiling or evaporation. Okay, there is actually a difference between evaporation and boiling. We're going to do that later. On a TS diagram, that is where we have a phase change. Okay. If it is a gas becoming a liquid, then we know it is condensation. If it is a liquid taking up heat so that it becomes a gas, then it is boiling. But what is very, very important is that this process occurs, let me think, let me use TP. TP is a constant. Okay, so TP is a constant. So if we look at this case here, and we would enlarge it, and that is the wall. Okay. And this is a point there, at that point there, and there's another point there. Then firstly, what we can see is that this temperature and that temperature, what happens with the temperature on the outside? The temperature remains constant of the fluid on the outside. You see that? Because it's a two-phase process. The temperature remains constant. So that temperature is equal to Tp, and that temperature is also equal to Tp. Okay. Then, what you're going to see, what also happens is that in condensation and evaporation and boiling, the heat transfer coefficients are very, very high. Usually in the order of tens of thousands. While in single-phase fluid, it is typically in the order of hundreds to thousands. So if we would now draw the resistances from here to here, then I hope you can see it. That's the first one. And I'm trying to show that it is very, very small. Okay, so a very, very small resistance, depending on the diameter of the tube, the thickness, and the type of tube, then that one is normally also very small, and that is going to be the other resistance there. And here it's going to be the same. Okay. So if you go and do calculations with a few of these values where this is a very large resistance, that a very small one, you're going to see that that temperature and that temperature is going to be, for all practical purposes, is going to be the same. So a constant wall temperature is the second category. Our wall remains constant because of this process on the outside with very high heat transfer coefficients. If the heat transfer coefficient is very, very high, remember that resistance is directly proportional to 1 divided by the heat transfer coefficient. So if the heat transfer coefficient is very, very high, then the resistance is very, very small. And the result of that is that that temperature and that temperature, for all practical purposes, are the same. Okay, one last thing that I need to do. If we now go and look at these cases and we consider flow through a tube. We consider flow through a tube with a diameter d. And we've got these two different cases, the one of a constant heat flux and the other one with a constant wall temperature. Then the results, if we plot it as x divided by d, and if we plot the Nusselt number for the h. H is normally for a constant heat flux. Nusselt number h means heat flux is constant. Then the results would typically look like this. It's a function of Reynolds number. So this is the Reynolds number of 10,000. There is the Reynolds number of maybe 2 10 to the 5th. Okay. So this would be for a constant heat flux. If we compare it to the case of, and now I use the yellow to indicate it is the Nusselt number if the wall temperature remains constant. Then what we will see is that in this region here, the results are not the same. The results are not the same, but as soon as the flow is fully developed, the changes are negligible or very, very small. Okay. Ladies and gentlemen, any questions?